Hey students, welcome back to Physics 2.6. Today we're going to talk about how displacement can be expressed in forms of velocity, acceleration, and time. So we're going to have some combination equations today that will make our lives a little bit more simpler when we're dealing with these types of displacement equations, okay? So one that you have seen before is distance equals rate times time. All right, distance equals rate times time, or velocity times time. So if we want to know how long we traveled, we would take our rate, how fast we were traveling, times the time we've been traveling it. So if we've been going 80 miles an hour for 2 hours, that means our distance or our displacement would have been 160 miles, okay? Because our rate was 80 miles for 2 hours. 80 miles per hour for 2 hours would give us 160 miles. So what we want to understand in these equations is how we can fit acceleration in here. How can we fit acceleration in here? So what we're going to do today is rearrange some of our equations using some algebra, knowing and getting acceleration into our equations to make our equations much more useful to us, okay? So the displacement idea here is the average velocity. The average velocity, if you're going at a constant acceleration, let's say you drop the pen and it's failed at a constant acceleration because of gravity from your hand to the table, the beginning velocity, the initial velocity, minus the final velocity will give us the average velocity because it's accelerating at the same rate that we can use that as an average. So our final velocity minus our initial velocity will give us our average velocity. Okay, so here's what we'll do here. We have our distance equals our rate. Here's our new rate. Okay, our new rate would be our average velocity times time. So just like we had this equation up here, distance equals velocity times time. Now we've broken that velocity into an average velocity. We've added a couple more variables here. We have our final velocity and our initial velocity divided by 2 because we have two variables here. Just like you would take an average of your test, if you have a 100 on one test and an 80 on another test, you'd add those two together. 100 plus 80 divided by 2, because you had two tests, would mean you have a 90% average, right? So here you're taking a average velocity here, and that's what we're calling equation number one. Now, what we need is what I call Dave equations. Dave equations, equations that incorporate distance, displacement, acceleration, and velocity. Dave for short. Okay, we want to get some equations that incorporate distance, acceleration, and velocity. Let me show you what I'm talking about. Here, this equation has some displacement and it has some velocity, but it lacks acceleration. It's got some time in it, which is helpful. This equation here has velocity and acceleration, but it lacks distance. Okay, so that's why they're called Dave equation. I'm going to try to get to what we're going to do is we're going to do some fancy algebra. I won't do this with you here. I'll do that in our live class, a little bit of the algebra with you. It's a little involved, but we combine equation one and equation two together, doing some substitution and some distribution and foiling and some square rooting and that sort of thing that we'll work on together. You do that and you get some equations, which I will call equations two, which I call useful Dave equations, okay? So depending on what you have in your problem, you can have a distance and you can solve for distance if you have final velocity in the time that it took. Okay, if you only have acceleration in the time, you can find the distance using these two. If you only have the final velocity and you have the acceleration and the distance, you can rearrange your equation. So these three equations, you're not going to have to memorize them right away. They are in your textbook in section 2.6. You don't have to memorize them right away, but we're going to be using those just like we're doing sine, cosine, and tangent when you should use them. These are just different forms of a useful, what I call a Dave equation. Okay, so these three equations we're going to do now in some examples. Okay? I'm going to try to do one or two examples with you as I label them with you. Okay, so let's start them together. So example number one, let's do some labeling here. Let's pick a color. Let's get in the blue range since we have a blue slide. Okay, here we go. All right, so here we go. Right here is what we have here is we have suppose a planner. I can't get this to go away. Go away, please. There we go. Suppose a planner is designing an airport for small planes, small airplanes, so a small airstrip. Such planes must reach a speed of 56 meters per second. So I'm going to circle what we've been given. 50 meters. So they must reach a speed of 50 meters per second before takeoff and can accelerate at 12.0 meters per second squared. What is the maximum length for the runway of this airport? So essentially what we want to make sure the planes are going fast enough, they have enough high enough velocity that they can take off before they run out of runway. That's a pretty important thing, right? So let's write down what we got. We'll write down what you got up here. What you got up here. And so velocity, so we have a velocity. They must reach this speed. So remember it says it must reach this speed. That's telling us that's a final velocity. So our final velocity is 56 meters per second. You see that? And they can accelerate the plane itself, the engine that it's in there, and the weight and all that. It allows it to accelerate at 12 meters per second squared. So there we go, okay? Now I'm gonna write down what I need, what you need right here. What is they asking me? What? That easy tells me what I'm needing, a question mark right there. What is the minimum length? So I need a distance, okay? So let's go find a Dave equation. Let's go find a Dave equation that has distance, final velocity, and acceleration in it. That's what we're looking for. We're going to go find us a Dave equation. So let's scroll back up here. What equation has distance, acceleration, and velocity in it? Right here, this guy right here. Distance, acceleration, and final velocity. So we're going to use that equation right there. So that's going to be the equation VF squared, final velocity squared, equals 2 times AD. So we'll get back our pen here. Let's get back our pen. Okay, so here's our equation, VF, and the whole thing is squared, so I'll put it in parentheses, equals 2 times acceleration times distance. Okay, so what we're going to have to find, we're going to have to solve this equation for distance. So distance, we rearrange our equation, would be VF squared minus 2A. Okay, so then we'll just plug in our numbers, 56 meters per second divided by 2 times our acceleration, which is 12.0 meters per second squared, and forgot that quantity has to be squared, okay? So enter into your calculator. You can pause the video if you want to go ahead and do that. 56 squared divided by 2 times 12. Okay. All right, so that would be our answer. So 56 squared divided by 2 divided by 12. It would be 130. 131 meters. So the length of that runway has to be 131 meters. That should make sense. Think about what a runway is. Runway is probably the length of a football field plus some more. So that's a 131 meters is almost a full length of a football or a full soccer field from end zone to end zone, goalpost to goalpost. That seems about right. Maybe a little bit longer than that. So that makes sense. Always make sure your answer makes sense. Okay, so we'll clear that and we'll do another example problem and then we'll be done for our examples today, okay? How long does it take for a car to travel 30 meters if it accelerates from rest, that's a key answer, from rest at 2 meters per second squared? So here we have a 30 meters is a distance, so that's a D. Accelerates from rest, so that's an A, acceleration. So we have D and A, and we have how long. That's what we need. We need time. So let's write down what we got. Okay, let's write down what we got. So hang on just a second. here. Sorry about that. I clicked my wrong button there. Let me click the right button. There we go. All right, so here we have a distance. This is what we got over here. It's going to be 30 meters. Okay, our acceleration is going to be 2.00 meters per second. And we're trying to find time. That's what we want. So we need an equation that's d and a and t in it. Let's go find a Dave equation that's d, a, and t. d, a, and t is right here. D, a, and t. Those are the three variables we need. So d equals 1/2 at. D equals 1/2 at. So we'll go back into here. Okay, get that up. So d equals 1/2 at. Now was it t squared? Now see, I don't even remember all these myself. So let's see. Yes, it's t squared. So I knew it was something. So I wanted to make sure I got that. So t squared. Okay. All right. So what we're trying to solve for is we need t. So we have to rearrange our equation so t squared. Do some algebra here. T squared is going to equal 2a. Oops, not that. That's a mistake. It's going to be 2d divided by a. Now, since this is t squared, to get rid of the square, we have to take the square root of both sides. So 2d divided by a. So now we have our time. We just have to plug and chug here, right? So we're going to do the square root of 2 times 30 divided by 2. And that's going to equal 60 divided by 2. And the square root of that equals the square root of 30. And the square root of 30 on my calculator is 5.48. So my answer is going to be 5.48 seconds. There we go. That's going to be our final set. We wanted the time. So how long does it take a car to travel from 30 meters per 30 meters if it starts at 0 and it accelerates 2.00 meters every second? It's going to take 4.8 seconds, 5.48 seconds, excuse me. So what I want you to really grasp is these equations, how to use these. Your homework is going to have you using these equations. So get familiar with them, write them down in a notebook, put them handy for you. You don't have to memorize them yet, but you do need to be familiar with them and how to use them and when to use them. Okay, that's it for today, and I'll talk to you soon.